Hi, my name is Nicolas Grimbaum Yamamoto. Today I'm going to talk about primordial high-energy neutrinos, which is something I'm working on with Thomas Ambi here in the University of Brussels, where I'm doing my last year of PhD. The general idea is to consider neutrinos that were emitted before recombination and after neutrino decoupling with distinctive features that could propagate up to us without being affected too much by interaction with the medium, so that we could see those features in the range of atmospheric and astrophysical neutrino energies in existing and future neutrino telescopes. I'll try to first motivate the subject, and then I'll talk a bit about the kind of distinctive signal we've considered, then show how there's part of the parameter space for which you can expect those sharp spectral features to not be affected by interaction with the medium, and then finally look at what part of the parameter space remains once you take into consideration the constraint that pre-exists on this kind of scenario. So there's not a lot of way we can probe the early universe uh, using standard model physics. If you go back in time, starting from today, you have the 21 centimeter cosmology that probes reionization time, for which we are collecting data as we speak now in observatories in South Africa or Australia. If you go a bit further back in time, you have the cosmic microwave background probing recombination time, and for which we are, of course, several sets of data and other running experiments. And you can go as far back as the neutrino decoupling, at which time you have the emission of the cosmic neutrino background. But the problem there is that those neutrinos are very low energy today, so it makes its detection very challenging. This begs the question of whether we could have some neutrino of primordial origin, so before recombination, that could be observable today if they were of high enough energy. This is what we mean by primordial high-energy neutrinos, or FINUs for short. Those FINUs, they are a very simple BSM scenario. All you need is to have some kind of heavy relic that either decays or annihilate into neutrinos, or in this case, because I like to advertise my cat, into a pair of neutrinos. And those neutrinos, they have a very simple fate. They can either redshift and never encounter any scattering with the background, so that they only lose energy due to the expansion of the universe. Or they could have interaction with the cosmic neutrino background, and that would imply some distortion of the spectrum, and you would end up with partial modification or erasure of the sharp spectral features that you're looking at. Here in our work, we've been concentrating on trying to characterize the parameter space in terms of lifetime, abundance, and mass of the heavy relic, which is viable to produce sharp spectral feature that would be in this first scenario where you have no interaction with the background, so that the sharp spectral features would be preserved, and that you could observe today in energies ranging from a few tens of MeV to a few PeV. So this is not a new, complete new scenario. There's been a few papers on this topic, going as far back as 1980 with Fenton and Glashow. But the first real study of this scenario is from Galmini, Gondolo, and Sarkar. By the time, of course, there was no data on astrophysical and atmospheric neutrino in IceCube and Super Kende. They also did not consider the interaction channel with the cosmic neutrino background, and most notably the main interaction channel, which is the elastic channel. Then there's been, in the last 15 years or so, several works that were very punctual and looking at some specific cases where primordial high-energy neutrinos could be interesting for phenomenological purposes. So here our aim is to gather all the information there is on the subject and try to brush up a general picture in terms of the parameter space given for the heavy relic to see what is the variable part of that parameter space for observation of primordial high energy neutrinos today. The kind of sharp spectral feature that we've been looking at, or on one part decays, that could be two-body, three-body, or box-shaped decays, where you see here on this left-hand side plot the spectra at production given in dashed lines. And because those decay do not happen at a single time in the history of the universe, but happen through a large range of redshift, you need to integrate all those decays to get the spectrum you would expect today, given in the solid lines here. On the other hand, you have the case of equilibrium annihilation that we considered, which gives you also a very distinctive and sharp signal, and that could originate from an initial population of asymmetric particle that start oscillating into antiparticle after a phase transition, so that you can have the start of the annihilation happening out of equilibrium. Of course, those spectra, they correspond to what you expect if there is no distortion of the spectrum. So if there is no scattering over the propagation of those neutrinos from the emission up to us. So what's important is to make sure that there is a variable part of the parameter space for which there is no important interaction with the medium. To get a feeling for this, we compute the average number of scattering that a phi-nu might encounter over the course of its propagation by integrating over the line of sight the average cross-section over the target distribution function and the target neutrino number density. Here, the main target is the cosmic neutrino background because of how abundant it is. And on this plot here, I show the line that corresponds to an average number of scattering of 1 for the main channel of interaction with the cosmic neutrino background, which is the elastic channel. It is given in the plane of injection time and injection energy of the primordial high energy neutrinos, so that anything below this line corresponds to the regime where you expect multi-scattering and where you have to be very careful about what you're doing. But anything above this line, you expect to have less than one scattering in average, so that it is safe to assume that sharp spectral features would be mostly unaffected there. Now we have a large part of the parameter space for which we could produce those sharp spectral features early in the history of the universe and have them propagate to us without being affected. But we have to make sure that this part of the parameter space is not already constrained from theoretical or observational argument. From observation, we're interested in the range of atmospheric and astrophysical flux because they are isotropic flux of neutrinos that we observe in Super Kamiokande and ice cube, ranging from a few tens of MeV to a few PeV. And in that range, we're just going to impose that the flux of our high energy neutrinos, for example, what you can see here in indigo, is going to be at most the value of the observed flux in Super Kamiokande and ice cube. And from this, you get an upper bound on the abundance of the heavy relic that decays into those neutrino, which is parameterized as a fraction of the dark matter energy density today. You also get bounds from more theoretical argument, first from delta NF as you're adding neutrino energy density before recombination. So in this plot, in terms of the lifetime and mass of the heavy relic, you also get a bound on the abundance of the heavy relic. And the NF bound is given by those horizontal contour that you can see here in the back. Then we have strong BBN constraint in that region for higher energies. because at those energies, the neutrinos are going to start radiate energy. They're going to start radiate gauge boson that can start cascade, whether they're hadronic or electromagnetic, that might spoil the abundance of light elements. Finally, from the same mechanism, you can spoil the CMB anisotropy bound, the CMB anisotropies, and get a bound because you are adding energy into the electromagnetic path and you might spoil the anisotropy power spectrum. Those constraints can be combined with a constraint from observation in this unusual plot in terms of the ratio of the constraint from theory to the constraint from observation on the abundance, which gives you a relative percentage of how much you can saturate the observed flux with your flux of phi news. So if you sit anything above 10 to the minus 2, so yellow, orange, or red, you will be able to have a phi nu spectrum that is allowed to go as at least at the percent level of the observed flux. So depending on your experimental sensitivities and your energy resolution, you might be able to detect those neutrinos in the yellow part and probably be able to see them in orange and for sure in red. So this is a large part of this same parameter space here that is potentially observable today. But you have to remember that there is a region in this space where you expect to have important interaction with the medium. So we recasted the line that correspond to one scattering in average in the elastic channel, and you see that most of that parameter space, you have to be very careful about what happens. But over this line, it is pretty safe, and you can see that this is still a large part of the parameter space that span several orders of magnitude in mass, abundance, and lifetime. And so here, you can see that it is possible to probe those high energy neutrinos in existing and potentially in future neutrino telescopes such as IceCube, Super Kamiokande, or Hyper Kamiokande and KM3-NET. And that in this part of the parameter space, you could see some short spectral features that could be emitted early before recombination time and could tell you something about the early universe. So the take-home message from this is that primordial high-energy neutrinos is a very simple BSM scenario that could produce a neutrino signal in the early universe before recombination with very distinctive feature that could propagate to us without being affected by interaction with the medium in a large part of the parameter space. And so that means that you could potentially observe something in the neutrino telescope that exists, whether they are IceCube or Super Kamiokande or the future one, that could tell you something about this heavy relic for a large range of lifetime mass and abundance of that heavy relic. And I'll just quickly show what we're working on at the moment, which is the follow-up from this project, where we are actually trying to look into this interaction with the medium. And as I was telling you there, you very quickly enter a regime where you have to be careful about what happens. So the proper way to try and compute the distortion on the spectrum is to perform a Monte Carlo integration of the neutrino evolution. And this is what we are working on. So I can show you a very preliminary result that I got a couple weeks ago. So for a set of benchmark point here, I'm going to zoom in. You can see that you get very different spectra today. So if you're sitting outside of the region where you expect scattering to be important, you see that you have almost no distortion of the spectrum. As you can see here, the dashed line corresponds to the spectrum you would expect if you had no interaction at all. So there is a bit of distortion for lower energy that correspond to earlier emitting neutrinos, which makes sense because they will have to they will have a longer distance to go before they get to us. Then, as you get close to the line of one scattering, you have significant scattering still at lower energies that somehow make the signal a bit sharper, but do not erase it. And then once you get into the gray area, you have some very strong distortion of the spectrum, and very quickly you erase and flatten out the spectrum. So this is still very preliminary, and we still have a few effects to add, but hopefully we will have our final result quite soon, so stay tuned. And with this, I'll finish my presentation, and I'll thank you for watching this video, and I'll be very happy to answer your question next week, and in any case, have a chat about this very exciting project. Thank you again.